Okay, so I have noticed that many people were asking questions about normalization, and many people are slightly concerned about the new handling that has been posted, and there is a few worries. So today, just like last week, we did a revision of SQL with exercises. Today we will do a revision of normalization, normal forms, functional dependencies, and all those theory that we have been learning. And okay, we have already seen with some examples. Now we will go through the whole of it. We will see the full story. I mean, how we get a candidate key, how we check whether a normalization is dependency preserving, whether it's lossless. Well, okay, maybe we know that, but yeah, how we check dependency preservation through computing closures, how we do the minimal cover, and how we do a normalization. And so after today's exercise, again, the assignment that has been posted, I think will look significantly easier, if it's not already looking very easy, and a lot of doubts will be clarified. So let's start this way. As usual, we're given a relation. We gave just letters for the attributes because we want to abstract. So the relation has attributes A, B, C, D, and E. And we are told, or as we know, maybe we're not told, maybe we just determine ourselves. But I guess we're able to do that based on our knowledge of the world. We can find out what functional dependency we think holds or should hold or is expected to hold in the world. So we know that the following dependencies are true. The set of attributes A and B, and by the way, here we use this shorthand notation, right? Normally we should have brackets A, comma, B, close bracket. But I think we understand each other very well with this notation, and we avoid all those curly characters or figures in the presentation. So we can communicate this way. We have two dependencies that start out from a set of two attributes. A and B determines CD, and A with C determines B, D, E. And the observative looker, or the observative attendant, will notice that already there are 5 attributes here, and in this dependency, all 5 attributes are involved. So things are becoming already clear from the very beginning. And in the other dependency, again, all attributes are involved. So if I ask you, do you see any obvious candidate key, I think you can very easily come up with the idea that maybe from the first two dependencies, maybe that one is a candidate key, or maybe the other one. But still, usually we are not just asking find any candidate key that is obvious and visible. We are asked to find all the candidate keys so that we know what is really going on. I mean, because once we know all the candidate keys, we know that every superset of a candidate key is a superkey. And it's very useful to know what is a superkey because the normalizations the normal forms we know about are defined in terms of superkeys. Yeah, which is actually a mathematically correct way to say candidate key because you are supposed to get rid of anything that is redundant, so you can just worry about the candidate keys. Similarly, as some people were asking in the forum, the minimal cover of a set of functional dependencies is meant to help you get rid of redundant things. So you're giving a large set, but you can find its minimal cover, and then you only have to worry about the minimal cover. That's the purpose. So if you want to worry about the full set, you can do that. You cannot get something wrong, but the minimal cover will make your life easier. So similarly here, we just have to find what is a candidate key. We don't need to find what is a superkey because a superkey is something redundant. It's a candidate key with more attributes. Okay, so let's define a systematic way to do that because I think that's what we want to learn today. To observe what is obvious is easy, or to just figure it out on intuition or whatever. But what would be the complete way to do that? That's what we are learning now in this revision session. So here is a general rule or a general algorithm to follow. We list all the functional dependencies that we know. By the way, at the moment we don't know if that's a minimal cover, but we don't care. We just want to find what is a candidate key. So we are fine with the set that we are given. And we try to compute the closures of each attribute. Well, by the way, that will not be enough. We don't have to compute just the closure of each attribute. We have to compute the closure of each single attribute, and then the closure of each set of 2 attributes, and then each set of 3 attributes, and so on, until we reach 5, because we only have 5 attributes. So that's the complete thing to do. That's the totally cover all cases thing, all case safe approach. And how will we compute the closures of sets of attributes? Okay, we know how to do that. We start with a set, and then we try to obtain everything that is functionally dependent on each set that we have. So for example, we want to compute the closures of A, B, C, D, and E. We look at those dependencies, and we check, is there something that is determined by A itself, A alone? Well, not here. No, that's not helpful because it's A with something else. Second one, again, A with something else. I don't see much dependent on A alone, but A itself is dependent on A alone. Then as far as B goes, is there something that depends on B? Yeah, okay, I found one. B determines C. Similarly, C determines B. So, okay, I can put something there for what I can already get from B and C. And in addition to that, I can also note that C determines D. So I can have 2 attributes there. And also 2 attributes determined by B. So I can do that as well. So if you proceed this way, that's what you get. So B determines itself. Yeah, and we have done a bit more here. So A determines itself. B determines itself as one functional dependency says it determines C. And as another functional dependency says, the last one, it determines E. How did we get D over there? Why did we include D in the closure of B? Yes, here is one. Yes? Right. Thank you. So did you hear that? So thanks to transitivity, we know that B determines C, C determines D, so we already put D there as well. And in reverse, or not in reverse, well, actually, yeah, we know that C determines itself, and B and D as well. And also, again, by transitivity, C determines B, B determines E, so we are free to put E at that set as well. The last 2 are not so well-endowed attributes, they just determine themselves. Okay, so we have 2 attributes that determine a lot, and 3 attributes that determine just themselves. And again, we can already see the pattern that emerges here. So the 2 attributes that determine a lot are quite strong, but they're not so strong to be a key at them as far as we know right now. Why? Because they don't determine A. Right. The other, among the 3 poor attributes, the last 2 ones are just dependent on the strong. So, okay, they're quite secondary. But A is an important other attribute because so far it has not been determined by anything. But okay, let's follow our systematic approach. So we said we will do everything systematically. So in the general case, we are not stopping here. We're not just saying, okay, I figured it out. Yeah, I see what's going on. The proper thing to do is to move to the next step and construct sets of 2 attributes. So there are 5 attributes in total, so they can construct 10 combinations, right? There are 10 combinations of 2 obtained from a set of 5. So here we have our 10 combinations. And now we can compute the closures How will we compute, what's the systematic way to compute the closures of those sets of two attributes? So what's the closure of A and B? Well, it should include the closure of A, united with the closure of B, and further united with anything that can be determined by everything we already gathered. But actually, if you just put the unions of those two, we already got 5 attributes, so there is not, at that point, we can stop. So there, yeah, you see the color. Here we gathered all attributes, we put that in orange, we underline it, yeah, we discovered a candidate key up there. Right, similarly, the closure of the set of A and C is the closure of A united with unioned with the closure of C, which again becomes all attributes. So there's nothing, there's no, I mean, at this point we can really stop. So here is a point where we stop. We discovered a set that has a subset of attributes that has the full set as its closure. So there's no step forward, right? There's no more to discover. Regarding the others, again, we follow this approach of putting the union together. For example, the closure of A and D is the union of the closure of A and the closure of D. It's just those two. And what do we do here? We look at this set and we try to find whether there is any functional dependency that we can derive from those two, I mean, and that has those two on the left-hand side. But we don't find any, right? So among those, there is no functional dependency with A and D on the left. Similarly, no one has A and E on the left. And then regarding the next 5 cases, all of them includes at least B or C or both of them. So all of them can be already set equal to this set of 4 attributes. Yeah, and maybe they include also some of those attributes. So yeah, the closure of those 5 sets is just this set of 4. And the closure of D with E is just this pair itself. Okay, so we have discovered 2 candidate keys already, and we have also determined, I mean, that's the news at the moment, we determined that there is no other set of 2 attributes that's a candidate key. That's what we know at the moment. And maybe now you will think, okay, so we can stop. Actually, we shouldn't stop at the moment either. I mean, maybe intuitively we see what's going on, but in the general case, to make sure that we have done nothing wrong, we are supposed to check whether there is a set of 3 attributes that's a candidate key, because maybe there is a set, well, of course there is a set of 3 attributes. I mean, that's a super key. If you take any of those 2 and enlarge it, you get a super key. But maybe there is some other set of 3 attributes that can be a candidate key. Right? I mean, what if you combine some of those other poor guys here that are not candidate keys? Maybe you get something. Right? So we have to try that as well. So we try sets of 3. Right? We want now to select 3 attributes out of 5, but actually we don't, yeah, we can limit ourselves, okay, we are not really so exhaustive as I am, yeah, we are exhaustive, but yeah, there are some things that we can, even in this totally systematic and exhaustive approach, there are some things that we don't need to do. At the moment, we don't need to check sets of 3 attributes that already include A with B or A and C, right? Why? Because we know that these are already super keys. So we are not worried about anything that includes those 2 as a subset, but we care about everything else. And so we have 5 combinations to worry about. How do we construct these 5 combinations? Well, we look at all the attributes that we have, and we try to create combinations that don't include A with B or A and C, and that's what we got. And we have to check the closures of those as well. Right? How will we do that? Again, we collect closures that we already have, and we put them together, and we create their unions. For example, the closure of this set of 3 attributes is going to be the union of A with D and T, so, okay, it's going to be AD. But the closure of those 3, it's going to be the closure of B united with the closure of C plus attribute D and its closure, and so on for the others. So here is what we get now. Okay, so the last 4, you see, have a bit, yeah, the last 4, since they include B or C or both, they already get that set as well. But you see, they didn't get, yeah, we have stayed, yeah, we enlarged, we have made sets of 3, they're a bit larger than the sets of 2 we had here, but still the closure remains just these 4 attributes. They didn't get any larger. Are we done? No. We have to check sets of 4 attributes as well. And again, we are not supposed to check sets of 4 that already include one of the candidate keys, right? So we don't care for sets that include A with B or A with C. And if you think about it, if you exclude anything that contains those 2, there is just this thing you have to worry about. And to get the closure of this thing, again, you compute the unions of all its components, and you just get itself. In other words, we are still missing A. Nobody can give you A, right? As we knew from the very beginning, A is an attribute that is dependent just on itself. B and C were strong, D and T were dependent on B and C. So here we collected everything except A, and we can get everything except A. So now we are done. Now we know that we are really finished because, okay, if we continue, the next step is just to get a set of 5. And the set of 5 is already the full set, the full schema of our relation. So of course, the full schema is a candidate key. We don't have to verify that. We know it. So right now, we see the full picture. So we tried all possible cases, while, okay, I mean all possible while excluding those that were really redundant, like those that already contain a candidate key, and we came to this conclusion. The candidate keys are these 2 sets. They're the set AB and the set AC. As I said, if you are observative, you can figure that out just by looking at the dependencies from the very beginning. But it won't always be so simple, right? In some instances, it may be a bit, you may have to follow at least a bit of this approach just to convince yourself that you are not missing anything. Right? For example, in your hunting, there are, as you have probably noticed, there are a set of dependencies that are a bit mixed with each other. I mean, attributes determine others, and then they're determined by them. So you have to, if you want to make sure you didn't miss anything, you have to do it this way. Right? Of course, there are ways. Okay, here, if you make the observation that attribute A is not dependent on anything, here is a valid observation, and it's valid to make this argument and to say, okay, I won't check anything more because the only thing that I miss is A, and A is not determined by anything else, so there is no way I can get A. That's a valid argument. Okay, you can use that. But as a general principle, the right thing to do, if you don't have any other arguments, so there are no easy tricks to use, is just to follow this approach. Fail-proof approach. You can't miss anything. You will determine your candidate keys for sure, and you know that the rest of what you do is going to be right. Right? Because if you are asked to get candidate keys and you get those wrong, then every other step of the process that you follow will also have errors. Okay, so that's the idea. Another interesting concept we have to know how to determine is the question whether a decomposition is dependency preserving or not. Actually, it's a bit similar to the previous concept. So when we calculate candidate keys, we have to see what's the closure of any set of attributes, and those that have everything else as their closure, or those that have everything as their closure. Those that have the full set as their closure, like it happened here, those two sets, those two pairs that have the full set of 5 as their closure are candidate keys. Similarly, if you want to find whether a decomposition is dependency preserving, you have to check whether the closure of all the dependencies you can see that hold within the component relations of this decomposition, whether the closure of all those is the same as the closure of the full set of dependencies. But computing a closure of a set of dependencies is even more troublesome than doing it for a set of attributes. I mean, with a set of attributes, okay, I just list a set on the one side, another set on the other, I'm done. With sets of dependencies, if we have to do closures, we would have to list everything possible that is redundant, and it may take too long, and it may be truly redundant. So another thing we can do is to check we are not missing anything. Okay, so the question is this decomposition dependency preserving? So we have 3 attributes here. Now we simplified a bit. The 3 attributes are A, B, and C. There is a functional dependency that A determines B and C. And we decomposed it to 2 relations. The one consists of attributes A and B, and the other consists of A and C. Okay, we didn't do too much. We had 3 attributes in a relation, and now we have 2 relations with 2 attributes each. They have A in common. It looks like a reasonable decomposition. Okay, what's the systematic way to check whether this decomposition is dependency preserving? Again, okay, if you are observative, maybe you see it already. Maybe you see what is going on by naked eye. Or maybe you don't. Maybe you're confused. Wait, maybe I have 2 arguments. One argument is, okay, here is a decomposition. I can see 3 attributes in it, but those 3 attributes are split. They're not together anymore. So maybe it's not dependency preserving. That's one argument. How do you like my argument? Am I right? Who says I'm right? Okay, okay, it's good. Don't agree just with what anybody tells you. So that's one possible argument. Another possible argument is, okay, we have a dependency that we need to preserve. There is just one attribute on the left. So it just says that this attribute determines the 2 others. And fortunately, I have put this attribute with the 1. Well, I mean, I have put A with B, and I have also put A with C. So, in fact, I'm not losing anything because I know that A determines B, and I know that A determines C. Right? I mean, the fact that A determines B is preserved in the one table, and the fact that it determines C is preserved in the other table. So, from that point of view, yeah, that's an argument that says it is dependency preserving. Right? Okay, but what's the systematic way, again, how can we just convince ourselves? Okay, so let's do it in a fully convincing manner. We have this relation, 3 attributes, A, B, C, and the functional dependency that needs to be preserved is that one. Okay, let's follow some steps. Let's find the closure of this set. And when we do the closure of a set, we do it in a standardized manner. We don't just write dependencies with 3 attributes on the right-hand side or whatever, in any form that they are given. We do them in following a particular pattern. We have agreed what the pattern is. The pattern is that we have singletons on the right-hand side. So the dependency that A determines B and C will be translated to 2 dependencies. One that says that A determines B, and one that says that A determines C. I mean, we have to extract those 2. We have to write them in this way. Since we are doing the closure, okay, we can also write the one we were given. And since we're doing the closure, yeah, we're supposed to write those that are totally trivial. Everybody determines itself. But okay, if we are observative people, we don't need, we can just keep that in mind even without writing it. So the important part, the generally important part that should not be missed is that we put everything with one attribute on the right. And if we have many dependencies, we also check what is transitive, what more is going on, and we construct all of that as the closure. Okay, but this case was simple. We can just afford to write the full closure in a redundant manner, so we know how the full systematic algorithm looks. And then we have this decomposition, we are told. We decompose that table to one with two attributes, and okay, then we have to ask ourselves, yeah, we see this table, and we have to ask ourselves, out of all the dependencies in the closure of F, which are projected to this table, so which are among the attributes of this table? That's how a dependency is projected. It is just a dependency that belongs to the closure, and you can find it, or you can express it as a dependency among the attributes of this table, right? Because it doesn't make sense to say that this table has a dependency that A determines C, because C is not there anymore. Okay, so for this table, we can really say that it has the dependency that A determines B. So that's the subset of the set of dependencies that is projected on that one. And on the other table, again in a very similar manner, it is valid to say that it has preserved the dependency, or it has projected on itself the dependency that A determines C. So that's how it works in general. And if those were larger tables and they had more attributes, you would do the same thing, right? So that's the general principle. Okay, so now we know that those two dependencies are preserved somewhere. And then what can we do? We can put them together. I mean, we put the set F1 and the set F2 together as a new set of dependencies. And we compute the closure of that set. Or, okay, maybe again, we don't write redundancies, but we have to convince ourselves that the closure of putting the closure that you get by the set that consists of these two together, F1 and F2, is the same as the closure of F. Okay, and I think in this case, I think we can convince ourselves, right? So if you put F1 and F2 together, you get two dependencies that A determines B and C, which are exactly the orange ones up there. And the orange ones are exactly the ones that are not redundant. I mean, everything else was either trivial or it was just the concise version of putting those two together. Okay, so I think we are convinced that indeed the closure of these two sets is the same as the closure of F. And since that happens, we can conclude that this decomposition is dependency preserving. Okay, so that's the result. It is a dependency preserving decomposition, and that's how you draw this conclusion. And I mean, that's how you draw this conclusion in general. Okay, now another concept that we learned about and we have to standardize our approach for is how do we get a minimal covers of anything. Okay, so now let's expand again our example. We have a relation with 5 attributes, and we have those dependencies where some attributes are strong and A doesn't determine anything and so on, what we had before. And now we have to find the minimal cover for this set of functional dependencies. So we are given 6 dependencies, and we have to check whether those 6 are, as few as they could be, or whether they can be expressed by omitting something. Okay, so what do we do? Again, we write them in a standardized manner. Okay, so those were the 6 that we are given. And out of those 6, the last 4 ones are already written in a standard form. I mean, they have a single attribute on the right-hand side. So we can read them, I mean, we can process them as they are. The first, the colored ones here, I hope you see that bright blue color. So the first ones are not standardized, so we should better bring them to a standard form. I mean, we should say that A, B determines C, determines D, and so on. So let's do it. Here we are. What was colored in orange produced a set of 3 dependencies colored in orange, and what's colored in bright blue produces another 3. So that's what we got now. Okay, so now we are talking in a more concrete manner. Now we can look at this set and check out whether there is something redundant in it. And actually, just by, as I said, so the observative among us, or the most observative, can already figure out, hey, there are a lot of redundancies going on here. Why are you saying that A with B determines C, since you're already saying that B determines C? So that one is redundant, right? And similarly, it's redundant to say that C determines D because C determines D. Okay, but let's do that in a standard fashion. So let's list all those together that we have and try to eliminate anything that can be eliminated. Okay. So, okay, let's start. Let's try, step 2. Let's try to see whether, there are many ways to eliminate something. I mean, one way to eliminate it is thanks to transitivity, or one way is to eliminate, to eliminate something because it is completely redundant as a dependency in full. I mean, it should completely go away. And another way to eliminate something is to find out whether it is the left-hand side is too large. Okay, but so let's check this one. Can we replace the dependency that A, B determines D by a dependency that says that B determines D, or A alone determines D? Right, so how about that one? Yeah, so as an example. Okay, who has a thought? Okay, I let you think about this for a moment. Yeah, so we are looking at the orange-colored one, and we are asking whether its left-hand side can be reduced. Would it be enough to say A determines D, or would it be enough to say B determines D? Yes. Thank you. I think that's a good point. So B determines D. I think with a little bit of inspection, we can find out that there is something that says that B determines C, then C determines D, so by transitivity, B determines D. So that's one approach to do. So yes, indeed. Thank you for the answer. So indeed, by the rule of transitivity, B determines C, C determines D, therefore we can already infer from the other dependencies that we have, we infer that B determines D. So that one can be simplified. Okay. You see, we didn't omit it yet. We just simplified it now, because then we have to decide exactly which ones we want to keep. Okay. So, putting it all together, we write, so we eliminated that one, and now we brought everything. That's one example. But so, putting it all together, we can, from that set of dependencies, we can actually infer what we got here. So by applying this principle in general. So the fact that A and B determine C is a redundant thing to say because the left-hand side is too large, you can just say that B determines C. To say that A and B determine D, as we just decided, can also be simplified because B determines D. To say that, again, those two determine E is, again, too much to say because you are already saying that B determines E alone. And for the others, yeah, you already have the fact that C determines B, so it's too much to say that to augment it with A. You already know the fact that C determines D, so again, that is too much. And for the last one, again, another application of transitivity, we know that C will determine attribute B. Attribute B determines E, so we can eliminate the last one as well. Okay, so by applying that kind of rule, we can reduce this set of 10 dependencies to this new set of 6. I mean, in other words, we keep those, the ones that were colored in white, and out of the others, yeah, we see that the other ones, all of them, they have a redundant attribute A in them. And if you omit the redundant attribute A, you just you get some dependency that we already had, right? Plus 2 dependencies that we didn't have. I mean, we have the dependency B determines E, that is a new and interesting one, and we have the dependency that C determines E. So that's what is really going on here. Okay, so we have reduced what is on the left-hand side. And that was the application of the principle that says you must try to make sure that all your dependencies do not have too much on the left. So that's one basic step that you do when you compute a minimal cover. Are we done? No, we are not done yet because we still have to decide whether, now that we brought everything into this standardized form, now we can decide whether something is redundant. Again, the observative observer will say that, hey, you could already decide that something is redundant. You could just drop that out immediately because you have that, or that's what you did. They say, well, actually, yeah, you can have many shortcuts, but the standard thing to do is to say that, okay, I write everything in this form. I have one attribute on the right, and then I just try to reduce the left-hand sides. Of course, if I get something that is already looks exactly the same like something else, okay, I don't write it twice, I write it only once. Okay, so formally speaking, what we did here is not that we dropped the dependency away. I mean, we didn't drop the dependency A, B determines C, we just reduced it. We reduced its left side, and okay, it just became the same like that one, so fine, okay. But now is the real moment of omitting something that we don't need. I mean, we can check whether some of the dependencies in our set of 6 is really unnecessary because we can just take it out, and we can still conclude that it's true by using the others. So the question to ask at this moment is, for example, can we eliminate the dependency that B determines C? Can we just get that from somewhere else? Right, what do you think? Can we get that from somewhere else? I mean, can the orange color dependency be derived from the white ones? Yes. Okay, I hear a no vote. Yeah, again, intuitively you are right, but then, yeah, when your set is so small, it's easy to convince yourself that you are right, but again, what's the systematic thing to do if the set is a bit larger and it becomes a bit hard to parse just by looking? Well, the systematic thing to do is the following. Again, you use our very friendly concept of closure. So you complete the closure of B based on what you got over there. You look at all the dependencies, and or you compute the closure of B even without, by ignoring this dependency. So if we ignore this dependency, and we compute the closure of B based on the others, we have that B determines itself, and okay, determines D and E. That's how it looks. So we didn't get C in the closure of B in that way, and that means that we are not able to infer this dependency from the others. So we cannot eliminate it, right? Omitting it, the set that we get if we omit the first dependency is not equivalent to the set that we have when we keep it. Second question, can we eliminate this one? Okay, let's follow a similar approach. We compute the closure of B by keeping this one away. What's the closure of B now? Okay, B determines itself. It determines C thanks to the first. It determines E thanks to the other dependency. And given that it determines C, we go a bit fast. We don't do the closure step by step. We did it at once. Given that it determines C, by transitivity, it also gets D and E. Right. And hey, wait a minute, what happened right now? We just got D in our closure. So yeah, we could already say that, by looking. So we have, by transitivity, we have that from B we go to C, from C we go to D, so we already arrived. So yes, the closure of B, even by excluding that dependency, contains D, so that dependency can be eliminated. It is redundant. And so by applying this algorithm in this way, in this order, right now we can eliminate this dependency. Now somebody might ask, what if I was checking them in another order? Well, that's a very good question. And I think that's the question that makes some people worry and ask, okay, what should I do? Which set should I use, this one or that one? The minimal cover that you can get, or that you will get, depends on in what order you do things, or on the order in which you do things. And so you may get a different minimal cover if you just process dependencies in a different order and you find that you exclude something else. And we have seen that already previously in our examples. But it doesn't matter, so that's the good news. No matter which minimal cover you get, it will be a correct minimal cover. So here we found that this one was redundant, and we eliminate it. So we continue now, and we check whether we can eliminate this one. Again, we compute the closure of B, if, provided that this one is eliminated. That one is, by the way, shaded because we checked it already. And the closure of B, by eliminating that one, will include C, B itself and C, and thanks to transitivity, it will include D and E. So again, we determined that the closure of B will include attribute E, even if we don't include the dependency in our set. So we can exclude that one as well. And then what do we have? Then we have, okay, eventually we keep the first dependency that goes from B to C, and we keep the other three ones. And okay, at this moment, just by simple inspection, we can see that any of those three dependencies that have C on the left cannot be inferred from the others, right? Because you can very easily see that the closure of C that you get if you exclude any of them doesn't include the attribute that is determined, right? If you exclude that C determines B, you only get, for the closure of C, you get D and E. If you exclude the second, again, you get the other two. The closure of C will always have just C itself and two other attributes if you exclude any of these three dependencies. And so, okay, we can now take a shortcut and we say that that's the minimal cover. We did some reduction, right? We started with a set of many dependencies, and now we have only that one as a minimal cover. And that's how you convince yourself of what is a minimal cover. And now we can take a break, and then we will talk about how to normalize all of that.